Okay. Okay, Assalamualaikum. Okay, everybody. So, for this video, we will continue on fluid mechanics chapter 4 on fluid flow in pipes and conduits. Uh, so, we will start. Okay, so the continuation on the derivation of Bernoulli equation. So, before this, we know Bernoulli equation in terms of pressure. So, the other part of Bernoulli equation is to make it more better, more simpler is by we represent it by in term of head. So we know the pressure head concept from the previous chapter. So the head concept means that we represent our pressure in term of H or head. So if you look at our Bernoulli equation after we divide the original the equation by G or by gravity. So now we get this new uh, equation, which is if you look, for example, if we divide we first the original one for the elevation part is GZ. When we divide by G, we leave only Z. So we know Z is the elevation, and now we know it is in meter. So meter, so we know it is on head atau OH for the elevation. But if you see the other two, so the pressure part and also the kinetic part, if we make the unit for these two, it also has the same unit. So with pressure divide by rho g, at the end you will get also the unit in meter. U squared, velocity squared divided by gravity, also at the end you will get m. So every part of this formula, the unit is m. So that's why we can represent Bernoulli equation in terms of head. So it also can be expressed between any 2 points on a streamline. So if we represent the Bernoulli equation at 2 points in a streamline, so we get this formula. So this is the for point 1, and this is for point number 2. So right now, what happened is the first part, which is pressure over rho g, is the pressure head. Height of fluid column that produce the static pressure P. The second part on U squared over 2G is the velocity head. So elevation needed for fluid to reach the velocity during frictionless free fall. And Z is the elevation head. Potential energy of the fluid and also H the total head for the flow. So the big H, the capital H, sorry, the capital H is the total head of oil. Okay. So usually when we want to uh, uh, solve any problem in fluid mechanics, we will use this form of Bernoulli equation, which is the heat form. So usually we will use this one, which means we have 2 points in one streamline. So we have P is the pressure, rho is the density, G is gravity, U is the velocity or average velocity, G is the gravity, Z is the elevation. But then to use this Bernoulli equation, we have some limitation or some condition that they need to meet. The first one, we need to make sure that the flow is steady. We know what is steady flow before from the first video. If the flow is not steady, we cannot use the Bernoulli equation. It's not valid anymore. And then the work is frictionless. So we neglect the friction effect. There are no shaft work. So we are not consider the work from, for example, from turbine or from pump. So there are no shaft work. We only consider what is happening inside the pipeline only, not from start from the pump in the pipeline only. So and then it is incompressible flow, which means that if we don't compress, the density will be the same because we know the density is equal to m over v. So if v doesn't compress the system, which means that we know that mass cannot be destroyed, will be the same, but what will change is the volume. So if the system is not being compressed, so the volume will be the same, mass will be cannot be destroyed, will be the same. So we have a constant density throughout the pipeline. And then there are no heat transfer, and it is applied along a streamline. So it's the condition for using the Bernoulli equation. Okay, by using Bernoulli equation, actually it is being used to make and to utilize the flow meter. So there are three types of flow meter, which is pitot tube, venturi, and orifice. Okay, so this is the first one, flow meter, which is the pitot tube. So the pitot tube, as we know, that is an L a tube being inserted into the pipeline and then facing towards the flow. So it is against the flow, it's not as the apa nama tu lamina experiment, which is they are injecting dyes before this. It is going with the flow, but then for pitot tube it is against the flow, and then it is usually attached to a U-tube manometer. So inside this pitot tube, it has one manometric fluid, which is the darker one. So we know that manometric fluid need to be in higher density compared to the one that are being transported inside the pipeline. Okay, so we know from previous video that at point 1 we have flow, so which means we have velocity. But then at point 2, when we have flow inside this pipeline, and then at first point it will push the fluid inside this U-tube manometer, and then we will have a different in elevation of the manometric fluid, and then the flow inside this manometric fluid will stop flowing, and then at point 2 there are no movement, which means there are no velocities. That's why we know that U2 is 0, because this is stagnant point. This is stagnant. It is stagnant. It is not moving. So by utilizing the Bernoulli equation, so at first we know that at U2 there are no movement, there are no velocity. So U2 is being cancelled out. Oh, what happened? Okay. And then, but U1, they still have velocity, they still have movement. And then P1 and P2 pressure at 1 and at 2, it is still exists. But then for Z1 and Z2, because it is in the same elevation. So point 1 and point 2 is the same elevation. So if we put the Z1 and Z2, it will cancel itself. So Z2 minus Z1, at the end it will be 0. That's why we directly cancel out for Z1 and Z2. So what we are still yet is, what we are still there is the P1 over rho G plus U1 squared over 2G equal to P2. So after some manipulation of the formula, we will get the first derivation, which is P2 equal to P1 plus half of the rho U1 squared. So if you want to find what is pressure 1, and then we know everything right here, we know where we get it. Okay. There are two. This is the normal, the one that we know, pitot tube, which is the pitot tube that has apa nama, YouTube manometer inside the pitot tube. So after some modification, which is what is P? P is pressure 1 and pressure 2. So pressure is equal to rho GH. So for 4.2, it is being referred to the pressure because of the difference of the manometric fluid. So for P2, we have density manometric fluid, gravity and H2. And for P1, we get the apa nama ni, rho GH1 with the density of the fluid, gravity and the elevation of height 1. And then after some modification, at the end, we will get U1 equal to square root of 2G bracket of density of manometric fluid minus density of fluid will delta H, which means the difference in elevation of the manometric fluid over density of fluid. So this is a standard formula for pitot tube to find U1 for density at 1. This is the standard formula. Or if we know U1 and then we want to check or to determine other value, you can manipulate it like this. So this is the first stereo for pitot tube. So there are second variation of pitot tube, which is it doesn't attach to a YouTube manometer like this. This is attached to YouTube manometer, but this one we have pitot tube with a straight line here, and then we also have a piezometer attached like here. So for this kind of pitot tube, the formula will be like this. Because for this one, it doesn't have YouTube manometer, so we don't have the difference in the manometric fluid elevation. But then we have the elevation of piezometer and also the pitot right here. So the delta H being calculated by H2 minus H1, and then it is square root of 2G times the delta H. So this is the formula, standard formula for pitot tube for this kind of pitot tube construction. And then the second one will be like this. Okay, so where we can find a pitot tube? Actually, pitot tube, we have it on our maybe not so normal in Malaysia houses. And then we have this one. This is pitot tube, and then this is pitot tube attached to a aircraft to measure the velocity flow, and then it is connected to the electronics. So it is actually being used, but not commonly being seen uh, uh, everywhere. Okay, you can try this question. So we know carbon tetrachloride with a specific gravity of 1.6 flow through a pipe. The differential gauge attached to the pitot tube shows a 76 millimeter deflection of mercury. So find the velocity. So we want to find the velocity. We have 2g, so the standard formula, because we have the deflection of mercury. So if you say deflection of mercury, so it is actually using this kind of pitot tube. And density of mercury, the density of manometric fluid, which is the mercury. So we get given as 13.6. So we know that just multiply by 1000. And then we have 13,600 for the density of mercury and minus density of fluid. So this one is times 1000. So we got 1600 kilogram per meter cube. And delta H given as 76 millimeter. But then don't forget to convert it because everything will be in meter. So this millimeter, so convert to meter first and divide by the density of fluid. You can try it yourself. Okay, the second flow meter that we have is the orifice. So orifice actually is an opening, a round opening. So there are two type of pitot tube. Here, no. Okay. So we can consider a small opening on a tank or on a container as orifice. So there are two conditions. So one like this. So for example, we have a tank, and then at this tank we have an opening right here at point number 2. And then when we have a opening right here, so we know that we will have a flow of liquid. So we can use orifice uh, apa nama tu concept to calculate what is happening on our tank and on our system. The second configuration of orifice is actually you have done it in your experiment. I think experiment number 2. We have pipeline like this, circular pipeline, and then inside there are some pokok benar. There are one like this. You faham tak? So from the side, it is will be like this. From the side, we can see it like this, like this. But then from the front, it is actually a circular one, just like a washer, a round washer, and then it is put in the middle of a apa nama pipeline. So like this one. So this is the construction of orifice, the ring one. So it need to be in vena contracta, which is it is constructed with a very pointy end up like this. So as we can see, we know that from verification before, we need to have 2 point in straight line, and these 2 point, after we do some measurement or some observation, we can know and we can calculate the value of the other one. So for the one with this vena contractor construction, the point 1 is will be on the inside, and point 2 will be on the opening on the outside. So by using Bernoulli equation, so the first step as Peter tube is we will observe what is happening. So for orifice, so at the surface at point 1, which is right here, or inside of this here. Oh no, this one. So when we have the opening at point number 2, there will be fluid going out very fast, it's right here very fast. But then if we compare with reference to the fluid inside the tank, the movement of the free surface going down is very slow. So we consider it is a tank lah. If we want to, we doesn't calculate for a bucket of water, but then a very big one. So this free surface is point number 1 will go down slowly. So we neglect it because it is very slow. It is nearly 0. It has value, but then it's very slow. So we neglect it. So we say that U1 is neglectable. And oh sorry, it is actually U1 right here. And then for pressure, why pressure is considered as 0? Because at point 1 it is open. So the pressure, there are no pressure gauge, only PATM. So pressure gauge is 0. That's why we consider this as 0. So P1 also is 0. And at the orifice or at the opening, the same at the opening. Uh, Also on the outside, so P gauge is 0. That's why we say that P2 is 0. But U2, we have U2 because at 2, the velocity are very high. So we still have the value of U2 and Z1 and Z2, which is the elevation right here and elevation right here, we still have because it is not in the same line, but then different. So it has value. So usually we take Z2 as the datum or the reference point, reference plane. So we say that point 2, this is 0. And then we have some elevation right here. So we have Z1. So this is Z1 and it has value. But at Z2, because we are using Z2 as the reference plane, as a datum, so Z2 is being referred as 0. So we take out the Z2. So at the end, what is still we have is Z1 and also U2 squared over 2G. So this is what we still has, and after some modification, we know that the velocity 2 is equal to square root of 2gz1. Okay, but then this is the value, or even this is the value of velocity, and also for orifice we also said it as the theoretical velocity. Okay, so if we have the value of the theoretical velocity, we also can convert it into an actual velocity. So by using CV or coefficient of velocity, so we need to have this number. So CV, so U actual, we can calculate the U actual by using the formula CV times U theoretical. Whereas the U theoretical, we get the formula from here and times CV, which is the coefficient of velocity. Because of the use of Vena contractor, so we doesn't have the actual apa nama tu area. So we can also get the actual area equal to CC, so coefficient of contraction, times the area of the orifice, because the renal contractor has a very sharp pointy shape. So at first we are using the tip of this opening, which is it is the uh, uh, actual area. Okay, and then we also can when we have u with this velocity and we have a the area, we also can calculate the discharge or volume flow rate. So we know that from video number 1 that Q or volumetric flow rate equal to A times U. So for if we and then for orifice we get the theoretical velocity, area also the theoretical. So how we can get the actual one? So the formula, so for the actual formula, so Q actual equal to A actual times U actual. So we know that A actual equal to CC times A orifice kan before this. A actual equal to CC A orifice. And then we times with CVU theoretical. Kan? For this we have U actual equal to CV times U theoretical. So at the end, we will get CC times CV times A orifice times U theoretical equal to Q actual. Okay. And then CC, when CC is being CC times CV, it will become CD, which is the coefficient of discharge. CC is the coefficient for contraction. CV, coefficient of velocity. When they are both being times together, it becomes CD. So that's what is right here. It becomes CD, A orifice, U theoretical. So at the end, how we can get Q actual for orifice? So Q actual equal to CD times A orifice and U theoretical, which is U theoretical from here times the 2GH. So for orifice, we have two formula. So number one is U2, U at point 2 equal to square root of 2GZ. And the other formula is the Q actual equal to CT times A orifice square root 2GH. There are two formula for orifice. Okay, you can check, you can try this question. And the last flow meter is Venturi. So Venturi is a device for measuring discharge in a pipeline. What is discharge? Discharge is the volumetric flow rate lah, or mass flow rate. So discharge. It consists of rapidly converging section which increase the velocity of flow and hence reduce the pressure. Then returns to the original dimension of the pipe by gently diverging diffuser section. So this is apa nama tu? Venturi. So this is the pipeline, original pipeline, and this is the original pipeline. It being cut here, then it cut here, and then they will put one venturi, which is the venturi is as before consists of rapidly converging section which increase the velocity. So right here there will be a decrease of sudden decrease of diameter, and then it will come back to the original one. So this eventually. So when we have when we have a smaller diameter section over here, so we know that over here, we will have very fast velocity compared to the original pipeline. So because of this difference of velocity and of course pressure, we if these 2 points of the original one and the venturi neck, we call it neck venturi neck over here, we will have the different and attached to the YouTube manometer, we will have the different in manometric fluid right here. So by using still using Bernoulli equation, and we put the Bernoulli equation together with continuity equation. So continuity, this is continuity equation, which is Q equal to AU. So we know that Q1 equal Q2 because conservation of mass before. Q1 equal to Q2. So U1 A1 equal to U2 A2. So at the end, we know that U2 velocity at 2 equal to U1 A1 divided by A2 because area 1 and area 2 we know we can calculate U2 after substituting the here, put it over here, and some after modification, and then we put the apa nama tu formula for the actual discharge over here together with the CD and everything. And then some other modification and manipulation of our formula. At the end, for Venturi, we get the formula for Q actual or the discharge or the volumetric flow rate, the actual flow rate, which is equal to CD, coefficient of discharge, area 1 and area 2. So because we know the diameter of point 1, diameter of the point 2, which is the neck of the Venturi. We know 2, gravity, and also H, the difference in the manometer tube. And then we know also the density of manometric fluid and the density of fluid that will flow in the pipeline. So we can calculate the Q actual. So this is the standard formula for venturing. Okay, you can try to do it this one. Okay, the other section for chapter 4 is on the flow measurement for notch and weir. So what is notch? Notch is an opening in the side of a tank or reservoir that extends above of the surface of the liquid. So a notch is actually like a gate at a water gate. So for example, we have this is our river or our uh, pipeline, and then we have this one gate over here being going upward, and then we have so not all the water will flow, only the top part of the water will flow. And for weir is like a notch but on a larger scale. So you usually find weir on river. So it is devised to raise the water level. So this is weir. That's also just like this one. So we assume in notch or weir, the velocity approaching the weir is small. So the velocity of the original, because we have this apa nama ni stop this stop the flow over here. So the flow of the river is small compared to the one over here. So this is fast. But then over here, point number one, the velocity is small. So we neglect the velocity. So, and velocity through strip depend only on the depth below the free surface. Okay. So when we also can measure the width and also the depth. So by substituting these two into our standard formula from here, so at the end we will get the Q theoretical for notch and weir over here. So this is the standard formula for chapter 4. Then after some modification, so before this is the Q theoretical, and after some modification by adding the coefficient of discharge of uh, before this, we will get the Q actual for notch and weir as CD 2 over 3B square root of 2G H. So B will be the width of on top of the weir or notch, and H is the height of the everything of the river. Okay. So for notch and weir, we have two formula, which is one Q theoretical and Q actual. Okay, and then now we go to the part for head loss, which is head loss is actually the pressure loss in our system. But this time for pressure loss, for this time we will look into the effect of the pressure loss, the effect of the friction inside of our pipe or our system. So there are two equations for head loss. One is Darcy-Weisbach and the other one is Hagen-Poiseuille. So for the first part, we will look into Darcy-Weisbach. It is proposed by Julius Weisbach in 1850, uh, which is being published in their hydrodynamic textbook. It is very important and widely used in hydraulic. It's enable calculation of head loss due to the friction within a given run of pipe, and it is valid for duct flow of any cross section and for laminar and turbulent flow. So we can use this formula for laminar or turbulent. So this is the first formula for pressure drop. Delta V equal to FL rho U over D2. So we already know everything. We know of this formula. We know pressure. L is the length of the pipe, density, velocity, and diameter. But what is F? So this is the first time we saw F. So F is the friction factor. Okay. We will look into friction factor after this. So after some modification on our original formula, at the end, we will get the Darcy-Weisbach formula to be this one. This is the basic formula for Darcy-Weisbach. So you need to recognize this one. So head loss for Darcy-Weisbach head loss, it will be FLU squared. L is the length of the pipe, or the length of the pipe that we are considering or we calculating. U is the velocity, D diameter, G gravity, and we have the friction factor. So what is friction factor? So friction factor is is the factor being calculated because of the friction. So why we have friction inside a pipeline? So we know friction come from the movement of the fluid and being gassed by the pipeline. So it is being related to the pipe roughness. So relative pipe roughness is the ratio of the pipe roughness, surface roughness. This can be written as K or epsilon. It is the same to its diameter. So relative roughness being calculated by epsilon divided by diameter. So this is epsilon, okay. This is the roughness. So this is some simulation of roughness inside pipeline. So there are different type of roughness and different value also. So roughness is here and the diameter is the full diameter of our pipe. So friction factor or friction, we get friction loss or the loss of pressure of head due to the resistance of flow in the pipe and fitting. It is influenced by pipe size and fluid velocity and usually expressed in feet of head. So that is friction factor. So how to determine friction factor? There are three situations, not three ways, but three situations. So the first situation, if the flow is laminar, we can calculate the friction factor as like this, using F friction factor equal to 64 over Reynolds number. So the first condition, if it is laminar, we use this formula. So friction factor equals 64 over Reynolds number. Okay, the second condition or situation is if we have smooth pipe. Before this, it is laminar. Here it is turbulent, but then the pipe is smooth. So the K or epsilon value, the relative roughness value is 0, smooth. But it is turbulent flow, we use this formula. So friction factor equal to 0.3164 over Reynolds number by the power of 0.25. Okay. But what happens if we have turbulent and the pipeline is rough? So for this condition, condition number 3, with turbulent flow and we have rough pipe, we need to use Moody diagram. So this is Moody diagram, which is 3-axis diagram. Okay. So first we look into the first one at the bottom. At the bottom is the value of your Reynolds number. Okay, for example, after we calculated our Reynolds number, we get about uh 20,000. So this is 20,000, make one line over here. And then on the right side is the relative roughness. After we calculate our relative roughness, which is the roughness over density, roughness over diameter, if we get one value, for example, the value is 0.004, we will use this line, and at the end, we will get the intersection between right here. Intersection between in Reynolds number and relative roughness. With this intersection, we make one line to the left, which is the left is the friction factor. We get friction factor here. So from here, you need to look at your at the scale over here. So at the end, we know right here is 0.0. Here is 0.03. 24. Oh, sorry, what happened? 0.034 for reflection rate. So we will try it again during our tutorial class. So modeling diagram, first we determine the Reynolds number, and then we know the relative roughness, and then after these two being collect together, and then we have the intersection point, and then just take it, make a line to the left. Okay, so that is Darcy Weisbach, which is for turbulent. And then the second formula for to check the head loss is for laminar flow, we are using Hagen-Poiseuille. So this is for laminar flow. So for Hagen-Poiseuille, the formula, the standard formula for head loss is this one, which is 32 times mu Lu over rho d2g. So if we get the laminar flow, we automatically will use the Hagen-Poiseuille. Okay, so we know that for head loss, or we call it now as the head loss as a major losses. So using Hagen-Poiseuille and Darcy-Weisbach, we get the major losses or major losses in our system. So laminar flow, we are using Darcy-Weisbach, and sorry, for laminar flow, we use the Hagen-Poiseuille, and for turbulent is Darcy-Weisbach. So this is the standard formula that we know before. For minor losses, which is from the piping system, include fitting, valve, bend, elbow, T-inlet, exit enlargement, and contraction. All of these will make or will create minor losses, which is smaller value of the head pressure losses. So this component interrupt the smooth of flow of fluid and cause additional losses because of flow separation and missing. So how we calculate the minor losses? So the minor losses formula is here. So it is still HL, which is head loss, but then minor one, equal to KL is the loss coefficient times U2 over 2G. So this is the standard formula. So U2 and 2G we can already get from the problem, but then how can we get the KL, which is the loss coefficient? So we can use this reference to know how to apa nama tu, determine the KL. So everything has its own value lah. So you can check on this here. For example, for the elbow right here, sharp one, it is 1.1. For a smooth band, it is either 0 with flank with 0.3, with threaded with 0.9. And then if you have 90-degree meter bend, it is 0.2. And so you can determine. Look at this one. Okay, so this is the end of the lecture for chapter 4, part 2 on fluid flow in pipes and conduits. I hope that you will try to do your tutorials and will help you to do good in test and also in final. Okay, so that's all for chapter number 4, part 2. Okay, thank you. Assalamualaikum.